All right, so we're going to start by doing a little bit practice of what we did last class with these aldol condensations. All right, so the first one is a very simple one, just using acetone, a nice small ketone. All right, for the second one though, this will be an internal aldol condensation. So your nucleophile and your electrophile will all be within the same molecule. So we're going to have our alpha carbon react with that carbonyl carbon, all within the same molecule. All right, that's what we would call an internal aldol addition. See if you can't predict the product of these internal aldol addition condensation reactions. All right, so when we're doing our aldol addition and condensations, it's helpful to make a copy of our aldehyde or ketone because we want to remind ourselves that one of these is going to play the role of the electrophile at that carbonyl carbon, and the other one is going to play the role of the nucleophile at that alpha carbon. And that nucleophile is going to attack that electrophile, forming our new carbon-carbon bond. Okay, so when we're drawing our product, I'm going to start by drawing that nucleophile. When I get to that alpha carbon and I draw my new bond, on the other side has to be that electrophile. Okay, my addition product is going to be that alcohol or aldol, right? We have that carbonyl group and the alcohol group, but since I have heat here in my list of reagents, what's going to be, instead of this alcohol group, what functional group are we going to see? An alkene, the carbon-carbon double bond, right? So in this addition of heat here, we get this dehydration where that alcohol group comes off and leaves behind a carbon-carbon double bond. Okay, and so this produces these aldol condensation reactions. So again, the addition is with the OH group. The condensation is where you have the dehydration forming your alkene. And these are called enones, or more fancily, alpha, beta, unsaturated, in this case, ketones. And these are really going to be a big topic of today's discussion. We talked a little bit about these before. We're going to go back and revisit that in light of everything else that we've learned and talk a lot about these enones. Okay? But the other thing we're going to see today, so we want to practice here, are these internal aldol addition / condensation reactions. These will occur anytime you can have an aldol addition / condensation that would form a 5 or 6 membered ring, right? We learned that these 5 and 6 membered rings are the most stable of all the ring structures. You're not going to form any triangles, any really unstable 3 membered rings through an aldol addition. But if you can form a 5 or 6 membered ring, you can have this internal rearrangement here, this internal reaction, okay? And so again, in order for this to be a 5 or 6 membered ring, my nucleophile and my electrophile have to be 5 or 6 carbons apart. My electrophile, starting here, is 1, 2, 3, 4, 5 carbons away from this alpha carbon, this nucleophile site, so I can get this internal rearrangement, all right? So when this nucleophile attacks this electrophile, what's going to appear? What am I going to see in my product? In this case, a 5-membered ring, but yes, a ring, right? So absolutely, we're going to get a ringed product here when I connect these two. And so I think the easiest way to draw these products is to start with that ring, because it's really hard to sort of, in your mind's eye, kink all of these single bonds, rotate them all about to form this ring here. So I think it's easier to start with the ring structure itself. And then we're going to go around and number 1, 2, 3, 4, 5. And we're just going to make sure that it matches our same numbering that we had in our original reactant here. All right, so based on my numbering scheme, and I'm not numbering it to name it or anything like that. I'm just numbering to keep track of who's who in my reaction. All right, so according to my numbering, carbon 1 was the electrophile, and carbon 5 was the nucleophile. All right, so that means that on carbon 1, I'm going to draw both the addition and condensation products here, just to kind of make a point. My addition product. Carbon 1, since that's my electrophile, it still has that methyl group on there, but it also has that OH group. And what else is my ring missing here? The other carbonyl group, yeah, that was on carbon 4. So again, just kind of matching my numbering, I can tell that there should be that carbonyl group on carbon 4. But again, this had heat, so really we should be drawing the condensation product. Where that OH group comes off and forms a carbon-carbon double bond. And so I have my condensation product with that double bond conjugated to my ketone, to my carbonyl group. All right, so if we have 2 carbonyl groups within the same molecule, we can see this internal aldol addition / condensation reaction that would produce one of these ring structures here. All right, so again, we're going to sort of spend a lot of time today talking about these alpha-beta unsaturated ketones and aldehydes, or enones, and a class of reaction we're going to call, well, we're not going to call it, everybody calls Michael's reactions. All right, so our Michael's reactions here, we've covered one already, so let's just kind of remind ourselves. If we have one of these alpha beta unsaturated aldehydes or ketones, all right, the one that we discussed was using a Gilman's reagent. Right, and these alpha beta unsaturated ketones, they have two electrophilic sites, that carbonyl carbon, but because of resonance, also the beta carbon in that molecule. Right, so two electrophilic sites. And Michael's reactions are reactions that specifically target one of these two sites, that beta carbon. So Michael's reactions are nucleophilic additions that target that beta carbon. Whoops. All right, so what we had learned is if we take one of these Gilman reagents, these will specifically target that beta carbon. All right, and in this case, we'll put that R group on that beta carbon. All right, and so specifically our mechanism here, I'm just going to use generic nucleophile for my nucleophile because we're going to sort of extend this. All right, my nucleophile is going to specifically attack that second electrophilic site, that beta carbon. All right, and that causes, through resonance, this big shift up to that oxygen. All right, so now I have my nucleophile attached. And this negative charge on my oxygen. And we talked a lot about these structures right here. What do we call it when we have this, what are we looking at here? This is an enolate. Okay. And so then the next step in this mechanism here uses that acidic medium there. So we can go ahead and protonate that oxygen. You could actually also do a resonance you could also complete this mechanism using the other resonance structure of our enolate ion. All right, but the bottom line is under acidic conditions, we can protonate that oxygen. And this gives us not an enolate, but an enol. Which under acidic conditions is always in equilibrium with, and this is an equilibrium that very greatly favors the ketone here, special equilibrium, what we call a tautomerization. All right, but yes, that enol will tautomerize back to a, in this case, aldehyde. All right, so we get that nucleophile being specifically added to the beta carbon, and so notice that allows us to retain our carbonyl group, right? We don't actually lose our carbonyl group when the beta carbon is playing the role of the electrophile. All right, so our reactant in this reaction here was this alpha-beta unsaturated ketone, or aldehyde in this case. All right, that is one of a few compounds that fall in this class called Michael's acceptors. This is a class of molecules that all have electrophilic beta carbons. Okay, and so they all have this same basic structure where you have this double bond that's conjugated to some electron withdrawing group. And so a carbonyl group, like in our aldehydes and ketones, those are examples of electron withdrawing groups. All right, but we could have a few other ones as well. So let's make our complete list here of electron withdrawing groups. Okay, so first of all, we have our aldehydes. And our ketones. Okay, but there are other carbonyl containing functional groups as well that we could have. So for example, an ester. We have that carbonyl carbon in that same position, but we have an ester that will also work. An amide is another carbonyl containing group. So we have a nitrogen on the other side. That would also work. Importantly, what's not going to be on this list is a carboxylic acid. Carboxylic acids have protons that are even more acidic than our aldehydes and ketones, and so they wouldn't be able to survive under basic conditions. All right, and then the other two are a little bit oddball. They don't have these carbonyl groups. The first one is a nitrile group, which we said behaves surprisingly similar to carbonyl groups. They can be reduced and oxidized, and in a sense that makes sense because you just have a carbon that's got this really high order bond with an electrophilic atom. It's just a nitrogen instead of an oxygen. All right, and then the other one we've talked about before in the context of electron withdrawing groups, and those are those nitro groups. And again, makes sense when you look at the structure. Oops. All right, so if any one of these groups is conjugated to one of these double bonds, carbon-carbon double bonds, it makes those electrophilic, it makes those beta carbons electrophilic. All right. Now, in these reactions, the other component are what are called the Michael's donors. All right, and Michael's donors are always highly stabilized carbanions. Okay, and that stability is usually through resonance. All right, so we've seen one on our list here, our Gilman reagent. But this is kind of an oddball, this organometallic compound. All right, all of our other, most of our other Michaels donors will have these really common, really similar features to it. All right, so let me just show you an example here. All right, so we talked about how if we have a ketone, that alpha carbon is relatively acidic. But if we sandwich that alpha carbon between two carbonyl groups, it drops the pKa down to about like 7, much, much more acidic. And so this would be this highly stabilized carbanion that we have here, stabilized by resonance, not just with one of these ketone groups, but with two of them. All right, and so this is going to be a really common feature that we're going to see with our Michaels donors. They have an alpha carbon that's sandwiched between two electron withdrawing groups. All right, so it could be, for example, this ketone, these two ketones. It could instead be with two aldehydes, or an aldehyde and a ketone, or two esters. All right, or even two nitrile groups. All right, all of these enolate ions here are sandwiched between, are not just near one, but two electron withdrawing groups, which helps stabilize that negative charge. And that really stable negative charge on that carbon is a really important feature for these Michaels donors, which again prefer that beta carbon of the Michaels acceptors. If it's too strong of a nucleophile, something like a Grignard, it will react instead with that carbonyl carbon. We're talking about reactions that specifically occur at this beta carbon here. Whoa. All right, so there is one sort of note that we're going to put up here, the little bit of an oddball, and that is if we have a nitro group. Nitro groups are just such strong electron withdrawers that you don't need two of them. You only need one. All right, one of them is enough to really stabilize that carbanion to the point where it will favor that beta carbon in these reactions. All right, so let's take one of these. Okay, and we're going to react it with one of these alpha beta unsaturated enones. Okay, we're going to first need to add some base to create our enolate ion. Then we'll add in our alpha beta unsaturated, or rather what we call now our Michaels acceptor. Okay. And then we're going to add in our acidic workup at the end. All right, so again, see if you can't predict our products based on what we just did before with our Gilman reagent. But now you're going to use our other Michaels donor here. Again, the nucleophile is that alpha carbon. And the electrophile is going to be the beta carbon of our Michaels acceptor. So I'm going to start by drawing my nucleophile. I'm going to draw that extra bond. So on the other side there must be my electrophile, that electrophilic beta carbon. So now I got to draw in these remaining 1, 2 carbons. And finally, my carbonyl group. All right, so again, we can count carbons. We got to double check. 1, 2, 3, 4, 5 from my nucleophile. 1, 2, 3 from my electrophile. All right. For our Claisen condensations and our aldol addition and condensations, if we go back to what we did at the very beginning, we talked about how we have this check for our structures where our new bond, if we start counting from that carbonyl carbon, we have this new bond that's always between carbons 2 and 3, this 3-carbon spacing that we can use to double check our products for both aldol and Claisen reactions. Similar for these Michaels reactions, your 2 carbonyl groups will always be 1, 2, 3, 4, 5 carbons away from one another. So you get this same consistent spacing here for these Michaels reactions as well. Or I guess electron withdrawing groups, not necessarily carbonyls. All right, so now what if we take this product? Let me try to... And now we're going to put this in conditions for under which aldol addition and condensations take place. All right, so we'll add in some more base here. These like to occur in ethanol. And then we apply heat. Okay. Notice that our products now have these 2 carbonyl groups in them. And because of that spacing of those carbonyl groups, I now have an electrophilic carbonyl carbon that's located 6 carbons away from a nucleophilic alpha carbon. All right, and so we can form one of those internal aldol addition / condensation products. All right, so everybody take a second, based on what we did at the beginning of class here, see if you can give me that final product after these 2 steps. All right, what size ring am I going to start with? 6-membered, because I got my 1, 2, 3, 4, 5, 6 carbons between these two. So start with our 6-membered ring. Again, apply our numbering. Really doesn't matter which way you go, clockwise or counterclockwise. All right, and so if I stick to my numbering on my reactant side, carbon 1 is my nucleophile, carbon 6 is that electrophile. Since we have heat here, we're going to get the condensation product, but just to sort of help illustrate, I'm going to draw both the addition and then the condensation product. All right, so on carbon 6, since that was my electrophile, I'm going to have that OH group. On carbon 1, that's my nucleophile. Carbon 2, I will still have that carbonyl group. And then on carbon 3, I got to add a whole acetyl group here. Okay, if we have the condensation product, then that OH group is going to dehydrate off and leave me with a carbon-carbon double bond. All right. So what we just did here was first one of those Michaels reactions. Followed up by one of those internal aldol addition / condensation reactions. All right, and these happened back to back. We call these Robinson unalations. And we got a lot of names today. The Michaels, the Robinsons. We'll talk about a stork enamine synthesis, all right? It's kind of a pain in the butt when we have reactions that are named after people because it doesn't really give you much of a hint of what's going on in that reaction, right? A Michaels reaction. What the heck is that? It could be anything. I kind of have mixed feelings about it. On the one hand, it's annoying. On the other hand, you know, Robinson's a Nobel Prize winner from like the early 40s. There are a lot of not a lot, there are a few scientists that are household names like Einstein and Darwin, but of course there are many, many more in the history of chemistry that were super important. So it's good to give this individual their dues, but yes, I understand that learning a bunch of names is a big pain in the butt, all right? But yes, we got two named reactions here. Our Michaels reaction, if we follow that up with an aldol addition and condensation, that's all what's called a Robinson unalation. Okay, so I'm going to pick another Michaels set of reactants here, another Michaels donor and acceptor, and see if you can get me my Robinson unalation product. right, so first we need the product of that Michaels reaction. And once we get that, we're going to do our internal aldol addition / condensation. so I got my Michaels reaction product here. I've connected my nucleophilic alpha carbon to the electrophilic beta carbon. Okay, and now if I look at my product here, I can see that I have this electrophilic carbonyl carbon that's located 1, 2, let me use a different color. 1, 2, 3, 4, 5 carbons away from my other carbonyl carbon. So check, check. That's an important check for our Michaels reactions. Whoop. But if I keep going, it's 6 carbons away from an alpha carbon, from a nucleophilic. Holy cow. I'm driving nuts. Go away. From a nucleophilic alpha carbon. Okay, so now I can have this internal aldol addition / condensation reactions. Again, for the sake of completion and to kind of show my work, I'll first do the addition product and then the condensation products. And I'm going to start by drawing a 6-membered ring, because that's my ring that will be formed in these Robinson unalation reactions. Let's just take a step back and note, we said that you can have an internal aldol addition or / condensation reaction that would produce a 5 or 6-membered ring. All right, that's true. But for these Robinson unalations, because the carbonyl groups are always 5 carbons apart, the only option is a 6-membered ring. That will always be the case for a Robinson unalation, because it's preceded by that Michaels reaction. All right, so then I'm going to just keep my 1, 2, 3, 4, 5, 6, and I'm going to keep my numbering the same here. Based on my numbering on my reactant and product, 1 is my electrophile and 6 is my nucleophile. That means that 1 needs the OH group. And now I just need to decorate this with all these other groups that were in that molecule. So on carbon 2, I have a nitrile. On carbon 3, I have a methyl group. Carbon 4, I don't have anything, but on carbon 5, I have another carbonyl. And on carbon 6, I need a methyl group. All right. So then when I do my condensation reaction, I'm going to have my dehydration to produce that carbon-carbon double bond. Okay, so one of these Robinson unalations is again a Michaels reaction followed by an internal aldol addition / condensation. And yes, we get some big ugly products out of this thing, huh? You're not like, oh yes, I see what's going on. So breaking it up into these steps is really important. The coloring of carbons, counting carbons as a double check, but also using these like numbering schemes. I'm not numbering to name it or anything like that. I'm just numbering it so I can keep track of who's who. Can be really, really helpful. All right? Okay, and so these reactions start with this Michaels reaction. And we talked about our Michaels donors. We got kind of a limited list here, right? I mean, we have these 2 random ones at the top, but all of the other ones require these 2 carbonyl groups. I need a dione or a dial or something like that, all right? So if we just had a regular old ketone or aldehyde, we can also make them into enolate ions. We talked about that. So let's just kind of take a second to remind ourselves what I'm talking about. All right. In fact, we had 2 different methods of creating enolate ions. Both of them require these very strong bases. You can either use the bulky base, LDA, at low temperatures, or the small base, sodium hydride, at high temperatures. All right, and you get different enolate ions depending on what you chose. Everybody take a second and draw me my enolate that we would get at low and high temperatures using these bulky and small bases, respectively. Right, that bulky base at low temperatures will prefer that more accessible kinetic product, whereas my sodium hydride, my small base at high temperatures, will produce the more stable enolate ion. Right, so I can make enolates out of regular old aldehydes and ketones, okay, but importantly, these are not Michael's donors. Michael's donors specifically react at the beta carbon of those alpha beta unsaturated ketones. These enolates right here are too strong. They're too good a nucleophiles. They will react with the carbonyl carbon instead. Much like a Grignard would. So a normal old enolate is too strong. All right, so then how the heck can we use a normal old aldehyde or ketone in one of these Michael's reactions? Don't worry, they found a way around, and this is what's called a Stork enamine synthesis. Okay, so let's take a ketone. We can't treat it with the base because that will just turn it into a strong enolate ion, not a Michael's donor. So the first thing that we're going to do is treat it with a secondary amine. All right, we talked about how amines react with aldehydes and ketones in our previous chapter. Everybody take a second and give me the product of this reaction here. I'll give you a hint. It's in the name. All right, so secondary amines will react with aldehydes and ketones to form what are called enamines. And these enamines are Michael's donors. They're weak enough nucleophiles to react specifically with the beta carbon in one of those alpha-beta unsaturated aldehydes and ketones. All right, so if we combine this thing with one of our alpha-beta unsaturated aldehydes and ketones, let me move this, maybe a little bit more room. All right. We will see our, in this case, it's this double bond that will attack that electrophilic beta carbon. All right. And that will direct that new bond specifically to the alpha carbon, because at the same time, this pair of electrons comes down on that nitrogen. And then over here, that kicks off this chain of events that produces that enolate ion. So everybody take a second to follow my errors. Hopefully not errors, but arrows, and give me the product of this step here. All right, so okay, specifically at that alpha carbon, we have our new bond. Now my nitrogen is double bonded with a positive charge. I have that new bond with my alpha carbons, so then on the other side must be that electrophilic beta carbon. Okay, so then I need to include the other 2, 3 carbons from my electrophile. Oh, so, sorry. At this point, we're not quite done yet. We have alkoxide, negatively charged alkoxide ion. Oh my gosh. Enolate. Jeez Louise. Okay, here we go. Here's the product of this step here. And we talked about how we can reverse these enolate ions in acidic conditions. Same conditions that we can reverse these enamine reactions here using an aqueous acid. So in the last step, that aqueous workup, or that acidic workup will convert my enolate back to a carbonyl group, but will also convert my enamine back to a carbonyl group. All right, so we're not stuck with an enamine in these reactions. It's going to be reversed back to that ketone group.
So question 3 tomorrow?
Okay. Okay. All right, so normal aldehydes and ketones are not going to be Michael's donors when we deprotonate them. They're just too strong in nucleophiles. But we have a way around it where we can use just any old aldehyde or ketone, and that is by first converting it into an enamine, which is a good Michael's donor. So then when we take our Michael's donor, our enamine, and mix it with the Michael's acceptor, we'll again get one of those alpha beta unsaturated, or I'm sorry, one of those Michael's reactions. All right, and again, we can check our product. 1, 2, 3, 4, 5 carbons away from one another. All right, so let's do another one here. Starting with a different aldehyde or ketone, we're going to use cyclohexanone. All right, and we're going to do one of these Michael's reactions by first, instead of putting base in, I'm going to put in my secondary amine, creating that enamine. Then I'll react this with one of those alpha beta unsaturated aldehydes or ketones, or any Michael's acceptor really, but we'll pick a alpha beta unsaturated ketone. And then the last step is that acidic workup. Okay, so see if you can't give me the product of our stork enamine synthesis. All right, so we could do it the long way and draw out our enamine and all that jazz, but really we're just doing the same thing we've been doing, which is connecting our alpha carbon to that electrophilic beta carbon in our Michaels acceptor. Okay, so when I'm drawing my product here, I'm going to start by redrawing my nucleophile, and I'm going to draw that new bond, so on the other side must be that electrophilic beta carbon. So I'll have one methyl group, but then also the rest, so 1, 2, 3, 4. I can double check 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 from my electrophile. And then my 6 from my nucleophile. I can see in my ring here. Oh, whoops, I somehow deleted that oxygen. All right. And now let's tie it all back around here. What if I took this and put it under these aldol addition condensation conditions? Put it back in basic solution. All right, so I have this electrophilic carbonyl carbon that's located 1, 2, 3, 4, 5, 6 carbons away from a nucleophilic alpha carbon. So I can have this internal aldol addition condensation reaction. Okay, so if I'm going to draw my addition product and then my condensation product, I'm going to start by drawing that new 6-membered ring. Okay, number that. I want everything to match here. So on carbon 1, that would have been my electrophile. And carbon 6 would have been my nucleophile, according to my numbering up there. Okay, so for my addition product, carbon 1 would have that OH group. Carbon 2, carbons 1 and 2 have this whole ring structure attached to them. So I drew my new ring that's formed. I also got to draw that existing ring structure on that as well. And again, if you look at the numbering of my reactants, you can see that it should connect to carbons 1 and 2. I also need a methyl group off of carbon 3 and a carbonyl group off of carbon 5. Whoops. Okay, and then for my condensation product, it's my addition product minus that alcohol group that got replaced with a carbon-carbon double bond. Okay, and that carbon-carbon double bond should be conjugated to that carbonyl group rather. All right, cool. So obviously these ones have some big ugly products. Again, keeping track of your carbons, counting carbons is a good check. These sort of technique of coloring the carbons that you're going to link is a good check. The numbering scheme that you use to make sure that everything matches, all these little tricks will be helpful since our products, you know, we're not swapping out a BR for an OH anymore or something simple, right? We're creating these big ugly ring structures here. So keeping track of who's who is really important. All right, cool. So that's going to do it for this particular discussion about alpha carbon chemistry. Next week is what? Spring break. Wonderful. So me as a human being, I very much so love spring break. I'm like, yes, we get a week off. Fantastic. Me as an instructor is always a little worried about spring break because I'm worried that students are going to check out or dump all this information that we've learned thus far and come back with an empty mind, all right? Let's just remind ourselves that we still got 7 weeks to go in this semester. So certainly enjoy your time off, enjoy your break, have a good, few days of relaxation, not leave Friday, turn off your brain, come back Monday kind of thing and haven't done any chemistry, all right? Make sure that you put in some study time. One other thing, we have our exam that following week. So you'll come in on Tuesday will be a review session. We'll just do some practice problems. And on Thursday will be that third exam. For this material and just kind of in general, we've gotten to a point in the course where there's a lot of information, right? So this sort of like attempting to memorize everything isn't going to really work too well, okay? I think when we're starting out and you're doing your homework problems, sometimes there's a tendency to like learn a little trick to get you to the right answer, right? Copy, paste, delete this, new bond here, oxygen, submit, right answer. Copy, paste, delete this, new bond here, oxygen, boom, right answer. And you're like, excellent, okay. That little trick, that's a great way to remember how to do something for like 5 minutes, all right? Learning a little trick is not enough for a reaction because maybe if we only had 5 reactions, you could learn a little trick for everything, but we're at like a critical mass here. Nobody can remember a million little tricks, all right? So having a better understanding of these reactions is gonna be really important to remembering them, right? Your brain just needs more information to hold on to. It's really hard to learn random facts, right? What's easier to do is to learn something and then build off of that foundation, okay? So if you're having trouble with a particular reaction, what you should do is learn more about that type of reaction. Turn to your textbook. But I know everybody's like, what, we have a textbook? Yes, we have a textbook in this course. It's free, it's online, you've had access to the PDF. If you go and learn a little bit, read a little bit about that reaction, it just gives your brain more information to hold on to, a little bit of context for that reaction, right? And that's just helping that sort of stick into your memory that much better. Or, I don't know, we didn't really do this back in my day, but you guys have YouTube now. I'm sure there are people who explain this stuff on YouTube, probably better than me, right? So somebody else to turn to, just a different context in which to sort of hear this information and get exposed to it will give your brain more information to latch onto, because it's too much to just memorize a little trick for every reaction, all right? So just sort of studying tip at this point, for a lot of these advanced courses, your outside of class study time, just being steeped in the material is really helpful to learning that material, right? I hope I don't suck at lecturing, but this alone shouldn't be the only bit that you learn about these reactions, or it's going to be really hard to retain that information is what I'm trying to get at here, all right? Okay, cool. So good luck. Have fun on spring break. Obviously, we have lab after this if you're in the lab course. All right, but yes, we'll break and we'll meet back here at 3:30 to start lab.